In this video, I'll show you how a user-defined template can be used to customize AIM for the simulation of a piping system. User-defined templates can be used for defining custom workflows and capturing engineering knowledge and best practices. I'll begin by selecting and executing a user-defined template. The template is now complete. It set up 3 simulation workflows, one for fluid flow, one for structural analysis, and one for modal analysis. By following the task workflow, AIM will guide me through the entire simulation process. I'll begin by selecting the import task and using the Fix option to select the geometry import source. Next, I'll select the Flow Physics task, and I'll use the Fix option to quickly navigate to the model input that requires my attention. Here I need to define the properties of the inlet boundary condition. First, I'll select the inlet surface, and then I'll use an expression defined by the custom template to define the profile and the magnitude of the inlet velocity. And then to complete the boundary condition, I'll define an inlet temperature of 50 degrees Celsius. Now I'll go ahead and execute the solution. I'll update the results task, and this will execute the solution and compute the fluid results. The results defined from the custom template are now available, and I'll review some of the key results from the fluid simulation. First, I'll review a contour of the fluid velocity on the fluid streamlines. This shows how the fluid flows through the pipe and around the valve. Next, I'll review the fluid wall temperature. Note that the average wall temperature is available as a named value, and it can be used in the structural simulation. Next, I'll proceed with the structural simulation. Notice that all the structural tasks are ready to update. I'll update the results task, and this will generate the structural mesh, execute the solution, and compute the structural results. The structural solution is now complete. I can review the deformation of the pipe from both the fluid forces and the thermal loads. I can also review the equivalent stress results, which show high stresses in the pipe supports. The next step is to complete the modal analysis. Again, I'll update the results task, and this will execute the solution and compute the natural frequencies and the mode shapes for the piping assembly. The template has defined the results for the first 3 modes of vibration, and I can review the natural frequency and the mode shape for each individual mode of vibration. Now that all the simulation steps defined by the custom template are complete, I'll show you more details as to how the custom template is defined. To automate location selection in the template, selection sets are imported from the geometry source, in this case space claim. The template defines a number of name values. These allow calculated data to be shared between different tasks in the simulation process. Named expressions allow parameters and functions to define pre- and post-processing properties. This expression defines the inlet velocity profile as a function of the pipe radius and is used to define the fluid inlet boundary condition. All of the fluid boundary conditions are automatically defined by selection sets in the template, except for the primary inlet velocity and temperature, which the custom template prompted me to input directly. All of the structural boundary conditions are also automatically defined by selection sets in the template. Note that the thermal load for the piping assembly is defined by a name value. This value is computed in the fluid flow simulation from the average wall temperature. For the modal analysis, the template automatically defines an expression to add the additional mass from the fluid inside the pipe to the density of the steel to compute the natural frequencies and mode shapes. The user-defined template can be used to simulate any number of similar design configurations. Here's an example of a different configuration of the piping assembly. Shown here are the flow results for the new design generated by the user-defined template. Shown here are the deflection and stress results generated by the template. And finally, the first mode of vibration defined by the user-defined template. To recap, in this demonstration, I've used a user-defined template to automate the flow, stress, and modal analysis of a piping assembly. Thanks for watching this demonstration of ANSYS AIM.